love to be able to, when we release the library, ship with it concurrent data structures supporting concurrent insertions that the user can rely on. But finding a one-size-fits-all solution is difficult because we don't know, as library authors, whether your program contains a large contended map accessed by many threads, or if it contains many small threads, many small maps that might be contended or uncontended. So given all that, what we end up doing is we expose alternative data structure libraries. We perhaps have a skip list map implementation and another implementation. And we can go on like this to finding data structure variants at the cost of work for us and complexity for our users. So the first of these data structure variants I want to talk about is a good old friend, the immutable data structure stuffed into a mutable box. So this is a great data structure that has a lot of wonderful properties, not least of which that it's extremely easy to reason about in a concurrent program. Now, since we ultimately want to build a mutable data structure, one might ask, why not instead start with a mutable, sequential, non-thread safe data structure and put a lock around it? So for this particular purpose, that is not a good choice. So there are some advantages of the pure data in a box. For one thing, you get a constant time snapshot of the entire data structure with a single read instruction. But more important for our purposes here is lock freedom. So if you use the appropriate atomic operations to access this mutable IO-ref location, you can build lock-free algorithms on top of it, which is great. For those of you who are Haskellers, ask me why atomic modify IO-ref is not suitable for lock freedom. In the case on the right, of course, we can't build lock-free algorithms on a data structure with a lock around it because a thread can be descheduled while holding the lock, and then other threads can't make progress. So that's no good. But neither of these is really what we want to talk about because we want scalable concurrent data structures. Both of these are bottlenecked by a single memory location that must be written by all threads. For speed, we need to implement scalable, lock-free data structures. And once we've done that, perhaps we're done. Perhaps we can use those for everything. I wish it were so easy, but alas not. Even in Java, where the Java concurrency library is quite mature and well-tuned, it still takes over twice as long to allocate a single concurrent skip list map as to allocate an atomic reference containing a purely functional map. So there's some disadvantages as well as advantages of these scalable structures. So perhaps a better mascot for them would be something like this. It's slow to get started, but very fast once it's going. And the problem with these concurrent data structures is not just that they're slow to allocate. They also take more bytes to represent the same data, and they can be slower in the single-threaded case. So you can imagine this is why Java didn't throw out all the sequential data structures when they added these great concurrent ones. Further, there are some implementation-specific constant factors to keep in mind. And in the particular case of Haskell and GHC, there's some extra garbage collection, generational GC-related costs to having mutable pointers as opposed to having immutable ones. There are more heap indirections for our mutable data structures. So those are all disadvantages to the concurrent data structure. The pure map in Elvish has a single mutable location, a single IO-ref, whereas our concurrent data structure is necessarily littered with more mutable locations. For example, the skip list has a logarithmic number of index layers, and each one of those has a linked list with mutable tail pointers. So there's a lot more red boxes on the right. Okay, so some of these disadvantages are language-specific. Some of them are more fundamental. Almost every algorithm for a scalable concurrent bag is going to store some kind of thread local state, thread local storage. And as soon as we do that, as soon as we store fragments of the data structure in these thread local locations, you can see that the initialization of the data structure is now more expensive. In particular, as the number of threads grows, we expect the cost to allocate and initialize this data structure to grow. And that's exactly what we see. Here in Haskell, for example, with GHC 7.10, if we're allocating one of our scalable maps, the cost of allocating a single map goes up from 20 nanoseconds linearly with the number of threads. And we can imagine that it will continue going up to 32, 64 cores, and so on. Whereas the cost of allocating a simple IO-ref containing the empty list, which is our sequential version of a bag, that stays flat, of course. So this is clearly a trade-off between concurrent and pure data, but is it really a problem? We can just present this trade-off at the feet of the expert programmer and say it's your job to deal with it. Unfortunately, that doesn't really work in this situation. And the problem is that we want to be able to handle situations like this. So if we have a concurrent map of concurrent maps, now the outer map is probably contended, but we don't know what the contention level is going to be on the inner maps. And it's not statically knowable. It's dynamic and data dependent, let's say. So this holds whether or not we've got a map of sets, a map of bags. The data structure doesn't really matter here. So in the experiments that I'm going to present today, we vary the access pattern on data structures like this to measure how well a given combination of data structures performs given a hot access pattern, which would mean all threads converging on a single inner structure, let's say, versus a cold access pattern where inner structures have somewhat equal probability of being accessed and therefore are unlikely to be contended. Okay, so our solution to handle data structures like this is a very simple mashup of existing data structures. So if you have an S1 data structure, which is pure, and a data structure S2, which is already a concurrent lock-free data structure, both of them having a simple API for inserts, reads, and removes, then we propose simply combining them in the following way. We have a single mutable pointer at the top of the structure. Our hybrid has a reference to a hybrid state here, which is in exactly one of three states. So we call the A state the starting state. That's our pure data in a box. And the B state is our final state, where we've switched over to the concurrent mutable data structure. So in the middle here, we have an intermediate state that I'll talk about in a little while. But the important thing is that we have the option to switch at runtime between one representation and the other. And when do we switch? When we detect contention. So the purpose here is to design data structures which optimistically choose the pure data in a box representation. But then if they experience contention in the form of failed compare and swap instructions, they will back off and switch over to the scalable variant. So the new operation is extremely simple to create one of these hybrids. All we have to do is create a new reference and fill it with the empty version of the S1 data structure. There's our mutable reference at the top of the structure. And as we do insert operations on the data structure, when it's in the A state, these are going to be directed to the S1 data structure, doing normal functional updates. And every write will need to mutate the pointer at the top. Reads only need to read the pointer, and they can proceed as usual. At some point, we detect contention, and we decide to switch into the AB state. Once we switch into the AB state, we initialize a new copy of the S2 data structure. And we also kick off a copy thread that runs in the background to copy the contents of S1 to S2. This sounds expensive, but it only happens once because we transition monotonically from A to AB to B and never backwards. So the copy thread, once we're in this intermediate state, writes all new information is going to go into the S2 data structure on the right. But reads are a little more complicated. You want to check if there's newer information in the S2 data structure, so reads first check on the right. But if it's not there yet, because of this background asynchronous copying process, we need to also check the old S1 data structure. Fortunately, that's very easy to do because the S1 data structure was pure, and we got a perfect exact snapshot of it at the moment we decided to transition, and that pointer is still valid, and we can still read the contents of S1. So this arrangement, this hybridization, depends on the S1 data structure being pure, and that's what I think makes it a fun application of purely functional immutable data. Okay, so at some point the copy thread finishes, and we've got all of our information moved over to the new structure from the old one at runtime. So at that point, we can finalize the transition by switching into the B state, swinging the pointer at the top of the data structure, and letting the garbage collector take away the old copy. So that's basically the transition. And the proof of correctness we've got in the paper depends critically on this monotonicity property that we never go backwards in these state transitions. It's also important that we have only one S2 data structure over the whole lifetime of the hybrid. So if you read the S2 pointer out while you're in this transitional intermediate state, that pointer remains valid for the lifetime of the data structure. There's a number of other small lemmas in the paper relating to the linearization points of the individual operations on the hybrid structures. I'm not going to go into those now, but the upshot is that we show that given a correct implementation of S2 and S1 individually, that this hybrid implementation maintains lock freedom and has correct set semantics. There's one more small wrinkle that I will cover before getting into the evaluation. So removals are a little bit tricky here. I gave you a sense of the insertion process, but for removals, we have to worry about how we manage the information in S1 versus S2. So let's take a simple history of the state of S1 and S2. We're in this transitional state. We start off with a map that contains values for X and Y. So because we're in this transitional state, AB, that means that there's a copying thread in the background that's migrating values from the left over to the right. So at any time, it can sort of pop values into the right-hand side here, such as x equals 3 over here. And then asynchronously, with that copying, we're also getting new operations coming into S2. So the user might write x while the copying thread is running in the background. And because that asynchronous copying thread, which is there primarily to retain lock freedom, must not change the semantics of the application, we actually need this copy and this write to commute. So if we had done these in the other order, we'd have expected the final answer to be the same. But how can that be? Well, to make that happen, the copying thread has to do weak updates to the S2 structure. So if there's already newer information in S2, the copying thread must not overwrite it. Because after all, the copying thread represents a snapshot of the old state of the thing and is subsumed by any new modifications. And this is true also of removals. So if we issue a remove y while we're in this transitional state, then we need to actually record the fact that we've done a removal. And this is what the concurrent replicated data type literature calls a tombstone value. Here we insert a tombstone value to say y is actively not here. And given that, the copy thread, if it tries to copy y over from the left, it just fizzles and does nothing. Now, once we finally transitioned into the S2 state, that isn't necessary anymore, and removes can be normal removes. One simple way to implement tombstones, of course, is just as a maybe value. All right, so now in the last few minutes, let's look at some more plots. So we already looked at the cost of allocating a scalable bag versus a pure bag. Let's update that one time with the including our new hybrid data structure as the red line. So as we can see, the hybrid data structure perfectly tracks the pure one. It behaves just as well as the pure data structure. Now, if we look at a contended insertion on the bag, so this is still a single bag, not a nested data structure. We've got all threads hammering on the same bag, trying to insert data at the same time. And here we're looking at the average cost of an operation. So lower is better. And we can see that the pure variants, the pure data in a box variants, are not getting a parallel speed up here. They're getting a parallel slow down. Individual operations take longer in the presence of more threads. And the reason there's two lines for pure here is we compared both the atomic modify IRF version, the traditional one, versus a speculative one that just uses raw compare and swap. Now, what we want to see here is that the hybrid gives us the best of both worlds. And here, it's not doing as well as scalable, but it is basically tracking the trend of the scalable data structure rather than the trend of the hybrid data structure, of the pure data structure. Also, very important is the one-threaded case. Because very often your software, which you ship, will run on one thread, and that's an important situation to optimize for. So here, on the very leftmost part of this graph, we can see that at one thread, the hybrid gets better performance than some of the alternatives. Now, pure insertion is a little unrealistic. Let's look at a mix of 50-50 insertion and removal operations randomized. So we see the same basic trend where pure falls apart at larger numbers of threads, scalable doesn't, and hybrid manages to track scalable. And again, we have that important property that the hybrid does well in the one-thread case. If we are running on a single-threaded runtime system, the scalable structure is imposing overheads that the hybrid structure is not. Our data set on the Haskell side is a little noisy here because the garbage collector has given us pretty non-deterministic behavior on these benchmarks. The Java ones I'll show you in a moment are a bit smoother. Okay, here's the nested data structure scenario that I promised you, where we have now an array of bags. So we have many, many bags in the inside of this data structure. And here's where we really want the hybrid structure to shine. So in our experiments in the paper, we varied this hot-cold threshold from 0 to 1. And this is the 50% mark, where we have half of our operations on the data structure targeting a single hot inner map, and the other 50% of accesses target the rest of the data structure with uniform probability. So in this scenario, we do, again, see the hybrid data structure doing better than the pure one as we go to larger numbers of threads, and also doing better than the scalable one at the one-thread point. So now, just to show that this isn't Haskell specific, let's go back to those Java examples as well. We implemented our benchmarks in both systems. So we already looked at the allocation costs of scalable maps. We can see that the hybrid allocation cost is not as cheap as the purely functional map, but is still cheaper than our scalable concurrent skip list map. We varied 10 different settings for the hot-cold ratio, but this is a map of maps benchmark in Java, and I'll show you just 3 points in that spectrum. So the first one is all cold, so all the accesses are uniformly distributed and none of the inner structures are contended. The other extreme is all hot, where all accesses go to a single contended structure. So this is effectively equivalent to benchmarking a single shared data structure instead of a nested one. Now the interesting one is the half and half option, because here's where half of our accesses are on the hot inner data structure and half are on cold ones. So here we see the hybrid giving us the best of both worlds and really performing the best of any option as we go to larger numbers of threads. One interesting thing that you'll have seen in some of the previous graphs is we do have a problem at the 2-core setting, which you can ask me about if you're interested. All right, so in conclusion, we've taken concurrent data structures, which are already quite slick, and shown how to combine them with purely functional data structures to add some new features. Here are my coordinates if you're interested in reaching me. At Indiana, we're always looking for new PhD and postdoctoral candidates, so please talk to any of us if you're interested. And thank you for your time, and I'll be happy to take your questions.
Questions? So one of the tombstoning is kind of interesting and works quite well for this particular data type. How well do you think that generalizes to other data types, other concurrent data structures?
So that's a good question. So tombstoning is a source of inefficiency for us because storing a maybe V is an extra indirection relative to storing V. But semantically, the concept is useful in a variety of areas. So it comes up a lot in the concurrent replicated data structure context, because wherever you have replication and multiple copies of a data structure, then you often need to record the fact that a removal has happened. So this is also, I suppose, a concept that's common from other areas like version control, where you never really delete something, you just record that it should be deleted.
Do you have any idea about why your hybrid one is slower than the scalable one in the larger cases? What is the extra?
Right. Well, we do have an extra level of indirection. We were always reading through that extra pointer just to get to the S2 and then call the S2 operation. So it really must be that, because otherwise we're just calling the S2 API directly. And of course, there's also the overhead to go through the pure phase and do the copy.
Right. And that tombstone, you were implementing that as a maybe?
Yes, and that's another source of overhead too. So 3 sources of overhead.
Okay.
Right. So there are a number of things we could do to maybe try to knock those 3 down.
Because that tombstone, that maybe is quite annoying, because 99% of the time you're not using it, right? It's
Absolutely. So Johan and Ed Komet have some work in progress.
Yeah, right.
We're going to have much more unboxed, immutable data on the GHC heap in the future.
In the hybrid case, when there's did you do any measurements of read latency while you're in the process of copying, or especially for the sort of really contended ones?
That's a great idea, and we have not done that experiment. So looking at a distribution of read latencies when you're in the scalable case, or in the transitional case, it must be worse, certainly, because you have to check 2 data structures instead of 1. But I would hope it would be not more than 2x worse. It's not locking, at least. You will make progress.
Some of the CIDT approaches have a problem with the add, delete kind of access pattern. Does that affect you?
Add, delete access pattern?
So if you delete and then add and then delete again, because the tombstone, you can't record.
No, I don't think that's a problem.